Hello everyone, I want to show you this piece of the Wasatch Fault Zone. Do you see as I move it back and forth, it shines, it reflects at us. Yeah, they're flashing at us. And you might also notice that there seem to be scratches on this surface too, and there are. These scratches here were produced when the rock that used to be above this piece that I'm holding in my hand, when it moved down relative to the piece I'm holding, which moved up, and that relative motion between the two, like this, produced the scratches that we're seeing here on this surface. So geologists have figured out how to go into the field and identify fossil faults. This is a fossil fault that was created during an ancient, very tiny little earthquake. Thank you. So where we live is about right here under, say, the T of United States. And you probably, some of you have learned in school already about plate tectonics, I'm guessing. So in plate tectonics, different plates, like the North American plate, is moving to the southeast, parallel to this blue arrow, relative to the enormous Pacific plate off to the west, that is mostly ocean, shown here in blue, but also has slices of Southern California and Baja, Mexico. So it does have some continental crust on it as well. And it's moving to the northwest relative to North America. So this pretty simple map here shows just one fault along the boundary between North America and the Pacific Plate. That is too simple, however. And one of the ways that we know that is that all of these purple dots here represent earthquakes that have occurred in about the last 50 or 60 years. And if all of the relative motion was occurring on the San Andreas Fault itself, the earthquakes would simply be lined up along the San Andreas Fault, and we wouldn't see this alignment on the east side of the Sierra Nevada mountains, called the Eastern California Shear Zone. And we also wouldn't see a number of faults that are in Utah along the Wasatch Fault Zone coming up to where we are here in Logan, Utah. This is an area of some considerable activity, and there's earthquakes occurring here. See, all these little purple dots represent earthquakes that have happened in the last 50 or 60 years or so. So going back to our location here in Logan, Utah, we are near the eastern edge of a big important province called the Basin and Range Province that is named for basins like Cache Valley and ranges like the Bear River Range or the Wellsville Range west of us. And if you drive from, say, Salt Lake City across to San Francisco, you will notice that you keep going up and down across basins and ranges on your way across this broad zone that is taking up a little bit of the motion between North America and the Pacific Plate. So most of that motion is occurring along the San Andreas Fault Zone that I put in here in thick redder lines, but we also have distributed very wide zones of normal faulting and extension and plate motion occurring far to the east of there as well. We see different kinds of faults west of this red line. Excuse me, west of that red line, we tend to see mostly strike slip faults with horizontal plate motions. And east of this line, we see a lot of what we call normal faults that produce basins and ranges and have vertical motion. And that's what we see dominantly here in Cache Valley. So this map only has a few of the largest earthquakes plotted on it. And we can see the topography now, this basin and range style of topography in this tectonic province that we call the Basin and Range Province. So next we're going to take a look at one exposure of the East Cache Fault in Cache Valley that was available for a month or two as a new trail was being put in south of the country club. There was an exposure of the East Cache Fault that is visible in this photograph in a vertical cut through Bonneville sediments. So what do we see in a fault that tells us that we're looking at a fault? You sometimes see very broken up rocks with scratches, which we call slicken lines on a surface. The rocks will change from one side to the other side of the fault because they've been displaced relative to one another. If you're on the landscape, you might see what we call an escarpment or a fault scarp that indicates a fault that's been active. And sometimes when a fault has been active for a very long time, like the East Cache Fault, we see mountains coming up on the one side of the fault and valleys like Cache Valley that have been dropped down on the other side. So let's go back to this photograph. You've probably been looking at it carefully and have figured out that we see 3 different traces of the fault here. And I'm wondering, can you pick them out? Here's a slightly better photograph. This is my hand trowel here at the bottom, just to give you a sense of scale. And I imagine that you have already picked out the 3 separate traces of the fault. There's one here, another one in this location, and a third in that position. So what we're seeing here are sands of Lake Bonneville that have been faulted down against uplifting clay, also deposited under Lake Bonneville on the right side of the photograph. Let's do another example. Here's a more complicated example that happens to be in a landslide, but faults look just like this. And what we're seeing is a whole series of small displacement faults. These are my gardening gloves here for scale. And we can trace originally low angle sedimentary rocks, these brown rocks. These used to be continuous and they've now been displaced along a whole series of small normal faults. And the biggest displacement seems to occur along this structure right here. And I'm guessing you've spotted that already because we see this white layer here that has been dropped down quite a bit, about 30, 40 centimeters or so relative to its continuation on the other side. So the red fault there has displaced this white unit more than any of these smaller blue faults that have shifted this brown sand around from one position to another. So now that we've looked at faults from the side, let's pull away and pull apart the fault surface and see what might be preserved there. Here's an example from Logan Canyon, and we see crystals that grew during faulting, and these are showing the relative motion of our side of the fault zone. It had moved up relative to the other side of the fault zone that's still preserved on the wall of the canyon. Other examples of fault surfaces are shown here. We see some mudstone that has been very complexly slicken lined. We have a polished surface here, and some slip on this fault zone went in different directions in the past. This is an interesting phenomenon that we see sometimes, that a fault surface will be slipping more than once in different directions from one earthquake to another. Here's a fault zone that turns out to be flat. So faults come in all sorts of shapes and geometries. They can be relatively low angle, like this one here. It has a bit of a curved shape. And when we first looked at this exposure here, we thought we saw a channel fill of this more orange sand that had filled this channel that was eroded down into the lighter gray colored rocks below. But when we went closer to the exposure and looked between these red lines that are showing the location of the fault zone, we discovered that there was smeared and striated clay that was preserved in this fault zone, and that this was clearly a fault rather than the base of a channel deposit that had been laid down on top of these underlying sands. We can see the sand from below coming up and being cut along this red fault zone, and there's a tremendous amount of very sheared up and smeared out mudstone, the dark rocks here within that fault zone. This again is my hand tool. It's about the size, excuse me, of a dinner plate or so. Faults can also be vertical. This is a strand of the San Andreas Fault here. They can be quite steep and have a single, very narrow trace. Sometimes they form what we call flower structures. On the right, we're seeing an example of that down low at the level of the wash. This is a fairly narrow fault zone, but the traces spread out and much like a flower in cross section, and it is much wider up at the top of the exposure. Here's another example of a flower structure. So sometimes faults can be vertical and have flat components at the very same time. The main stem of this flower structure is a steep one in this exposure, but there are also parts of the fault that spread out and have quite a low angle geometry, as we're seeing here. So we call these flower structures. Sometimes, as we saw already, mudstone and weak rocks can be smeared, clay can be smeared out along a fault zone, and that produces this dark layer that we see within this particular fault zone. This is called the extra fault zone. This happens even along the San Andreas Fault Zone that we're seeing here in a famous locality along Salt Wash. And you can probably see this red mudstone in the fault zone itself that has been smeared along as the green rocks on the North American side of the fault have been moved to the right relative to the tan rocks on the Pacific side of the San Andreas Fault Zone. And within the fault itself, we have this very smeared out red mudstone that is preserved. In the drone view by my colleague Mark Bunz and his students and I, we can see that smeared out mudstone quite clearly here. This is a truck in the wash for scale, and railroad tracks are in the corner of the photograph, just so you get a sense for how incredibly large this smear of red mudstone is that has occurred along the San Andreas Fault. Next, I would like to share with you a little bit about what we have learned from trenching and digging deep slots across active normal faults in Cache Valley. Here we're seeing a view of the East Cache Fault in the distance. The part that's next to Logan has been active in the most recent time, in the last 10,000 years or so, but there's been few large earthquakes documented on the rest of the normal fault, which is quite a surprise. So let's take a look at what a trench is like. We will first look at a trench that was dug by James Evans and Jim McAlpin across the southern segment of the East Cache Fault. And then we'll take a look at a trench that was dug farther north near Logan. Here's the southern trench. This is Jim Evans, the researcher who led this effort. And we're seeing the East Cache Fault separating the darker gray rocks closer to the photographer, and faulted down on those are more orange sediment that are part of the valley sequence. And there is a white brecciated and altered zone along the fault itself that nicely marks the location of the East Cache Fault. What was learned and what was described to visitors here during the trench review is that this part of the fault zone has had very, very few recent earthquakes, and it does not appear to pose a significant hazard to the residents of Cache Valley. The central segment of the East Cache Fault, in contrast, has had some Holocene major earthquakes. We also found evidence for interesting landslides like the one shown here that slip downhill. So landslides are another hazard. They're often triggered by earthquakes, and so identifying landslides in some of these trenches, as was done here, provides other important information about the risks posed to citizens of Cache Valley. The trenching that we just looked at was along this part of the normal fault between Logan Canyon and Green Canyon, is just off the slide on the left. And we were able to identify the precise location of the East Cache Fault in one or two of the many trenches several trenches that were dug in this region here in advance of neighborhoods being put in and developed here. And the purpose of the trenching is partly to identify where the fault is so that roads and parks can be placed on top of the active normal fault, and so that no one ends up with their home situated in a hazardous location as like on top of the normal fault. The information that we've learned in Cache Valley suggests that earthquakes here can range from being high 6s, 6.6, to low 7s, magnitude 7.4. Is the largest estimated magnitude of a paleo earthquake that's been identified in Cache Valley. And we also know about the timing of these earthquakes, sometimes precisely, as in these two examples. These are fairly well constrained for the ages of a paleo earthquake. And sometimes we just know a general range of time. This gray bar represents the time during which the Dayton-Oxford normal fault probably ruptured to the Earth's surface. So when we put all of this together, we see then evidence for about 4 earthquakes in the last 7,000 years, which comes out to a little bit more frequent than once every 2,000 years. So our risk of a major destructive earthquake in Cache Valley is significant, but not as significant as it is along the Wasatch Front. We've also learned that there are many more normal faults in Cache Valley than we had originally identified. And part of this is due to some very high resolution new information called LIDAR that allows us to see the exact shape of the land. So in 2011, these were the faults that we thought were active in Cache Valley. And we have added many additional structures to that inventory. This is work I've been doing with students, colleagues at USU and the Utah Geologic Survey. And one of the first discoveries was an important one. We identified a long section of the Dayton-Oxford fault zone that has ruptured to the surface in the Holocene. Prior to our study, it was not known that there were any Holocene ruptures, major earthquakes on the Dayton-Oxford fault zone, which we see here. And part of the reason that that fault zone had not been recognized as having this hazard is that in the valley, the southern 20 kilometers or so had not been identified previously because it becomes a dispersed fault zone and many small, low fault scarps take up the displacement across this area, and no single escarpment is particularly impressive. When we gather up all of the information into the main fault zones, we find that the West Cache Fault Zone consists of the orange, yellow, and red faults all together, acting as a series of structures that are extending the crust in a roughly east-west direction. The Wasatch Fault to the west is shown in green here as well. We have known the existence of the Wasatch Fault for quite some time, but the LIDAR data allow us to refine its location and history of displacement. And then the East Cache Fault Zone to the east is shown in the blue color. Now that we've seen how frequent earthquakes are on the Wasatch Fault Zone in the central part, which is the most active part, let's go back to Cache Valley and compare the frequency of earthquakes on the Wasatch Fault Zone, its central parts on the left, with what we know so far about the frequency of earthquakes in Cache Valley. Remember, there's only been one earthquake in the last 7,000 years on the East Cache Fault and perhaps 3 on the West Cache Fault Zone. And when we put all these numbers together, we find that there is a frequency of earthquakes in Cache Valley that's just a little bit more frequent than once every 2,000 years or so. And so the difference in the ratio is almost 6. There's almost 6 times as many earthquakes that occur somewhere on the central segments of the Wasatch Fault to every one major earthquake that we have documented in Cache Valley so far. So what are we to do during an earthquake? Here's a list of do's and don'ts, many of which are really best described in videos like this particular one here that you can access through the Shakeout website. Some key things is to drop, cover, and hold on. Stay inside. Don't run outside because hard materials like bricks tend to fall off buildings and often kill people, and stay away from windows. Here's a list of some of the excellent information that's been put together about earthquake safety and protection, preparedness, and so on. And we'll put this information on the geology website for you as well. So thank you again for your interest in faults. They are quite fascinating features in the geology, and I have enjoyed being able to tell you about them. Thank you.